We are live on YouTube, sir.
Okay. So yeah, hello students. I hope you can hear me. Okay, so if you have any questions, please go ahead. Okay, please unmute yourself when you speak. Uh, by the time people are joining, I can probably look at the questions which has come on the forum, and I'll try answering those questions. And then we can probably take more questions from you on YouTube or on the Gym link. Okay, so first of all, I hope that you are able to enjoy the course. It is meant to basically give you a flavor of CFD, starting from like how to build the Goni equations, how to code them, and how to basically use them for a realistic fluid flow simulation. Okay, so right now you have gone through 4 weeks, and the 5th week material will be added today. Okay, so I have got some questions, some queries from you, and which are very nice questions. So let me try answering some of those questions. Okay. So one of the questions was from Arpit Bundela, and he was asking that can we use CFD for simulation of fluid in space, like in places around black holes, star-forming regions, and galaxies? Okay, so definitely we can. I mean, we do CFD in those regions also, but we require some more consideration when we are talking about the flow in space. So as you know that the particles are highly sparse, right? They're not very close as you have in the fluids. Okay, we have talked about the difference between solids and fluids, and also between gases and liquids, right? The intermolecular distances. Right. So if you go to spaces, they are even more farther, right? So it may so happen that they will not follow the continuum, right? So if you're trying to use Navier-Stokes equations, that may not be applicable for the solution there, right? So there are other approaches which are used, which can be basically which can simulate a non-continuum flow also. So your equations will change, but the kind of schemes that we are discussing, right? So ultimately, it will be some kind of partial differential equations, right? It may not be Navier-Stokes, it may be a Boltzmann equation, it may be an equation which is solved. It may be Navier-Stokes equations, okay, to have the momentum transfer and those kind of things, right? So the principles that we're learning, the schemes that we're learning in this lecture will be useful. But remember that when we go to a place like a space where the continuum is not valid, so you have to have a special consideration. You may have the sleep velocity. Same thing happens when you go to the hypersonic regime also. Okay, in the hypersonic regime also, if the Mach number is very, very high, then your Navier-Stokes equations may not be valid. Okay, so then you have to look for equations which are valid for discrete flows also. Okay, that was one question. The second question was again from Arpit Bundela. He says that I have a question about what is happening in the video, and he's given a link for the video. And it says we need only conservation equations or principles. Can we model all the fluid phenomena using these principles or equations only? So if you've gone through our equations, you know that we use the mass conservation equation, momentum conservation equation, and energy conservation equation in a typical compressor flow. But still we know that the system is not closed, right? Because you have 5 variables. Let's say it's a three-dimensional flow. So then you have density, you have 3 velocity components, and then you have the pressure, right? And then you will have a temperature also. So there are overall 6 components, right? So to close the system, you need another model, right? Which is given in our lectures as the ideal gas equation, right? P equal to rho I T, right? So you need conservation equations, but also you may require some model to close the system. Similarly, we will see that when we go to very high Reynolds number flows, the turbulent flows, as you know, okay, then you'll be using some kind of turbulence model. Okay, if you want to solve in a model way. Okay, so there also you may have to play around how to get the eddy viscosity or turbulent viscosity, which may not be from the first principle. Okay, so the mass conservation, momentum conservation, energy conservation, they are from the first principle. Even in the momentum conservation equation, if you see, you have the model for the viscosity, right? We have talked about that the viscosity is actually a tensor with 81 components. We reduce it to one single component, right? So and we further give the modeling, and we say the bulk viscosity is equal to 0. And that's how you relate the second coefficient of viscosity with the first coefficient of viscosity. So the modeling is involved, because if you do not do modeling, the energy equations, the conservation equation by itself may become very, very complicated to solve. Right, but the primary principle, despite those modeling, is basically having satisfaction of the mass, momentum, and energy conservation. Okay, so this is the second question. I hope I'm able to answer that question as well. Okay, there is a question by Amit Pant. I have a question about what is happening in the video, and he's given a link for the video. While monitoring a CFD solution for convergence, the calculated quantities, energy, velocity, density, etc., monitored at how many nodes of the mix. Okay, so this conservation plot, convergence plot, you will see in every software, whatever software you're using, whether it's Fluent or OpenFOAM or CFD++ or Star CD or whatever. Okay, all the software console. So basically, it's an overall convergence, right? So you may have millions of grid points, right? So you will basically calculate the density there. You'll take some kind of average there, and then you will have the value from the previous time step, and you will see that how much difference that you have been getting, right? So if the difference is overall difference is going down, then of course you are going towards the convergence. Right, that's the idea of a steady state flow. And you will see these kind of plots only for the steady state flows, right? Because if the flow is unsteady, then if you try to plot this, you will have some kind of fluctuations or wiggles in your convergence plot, because it will go up, then go down. Okay, so that's one thing to remember, that this is some kind of overall measure of the convergence quantity inside the entire domain, not at a particular domain. Okay, in fact, if you're doing, let's say, LES, right? So then what you do is you put point probes at different locations. So LES is large eddy simulation, which is not the steady state. So there you put probe, and then you see that how the behavior is changing in the probe. Right? You may have pressure or velocity or density, and you will see that initially there is maybe a random behavior depending on initial condition. So that we call a transient behavior, and then you will start seeing some patterns. Okay, it may not be going constant, but it will be going up and down, and it may have some frequency in your probe monitoring also. Right. So based on that, you can determine whether you have reached some kind of statistical state or not. Okay. So to answer your question briefly, in the RAN simulation that you see, the convergence is the overall estimation of your density, velocity, and the pressure, okay, and how they are changing with iteration. Okay, yeah. There is a question by Ankur Parekh, and the question is that why is it that always the experimental on which you should rely more than the CFD? That's a good question, and see, typically when you do an experiment and you are doing a careful experiment where you are basically making sure that whatever errors that you have because of, let's say, the wind tunnel, or because of your instrumentation, so they are taken care of and you got the data. So if you have done an experiment carefully, then the results that you are getting is basically what is happening in the flow, right? So that they are typically considered as the true model. And the CFD, why you need a validation with experimental data, is because ultimately you are solving, you are discretizing a set of equations which are the conservation equations, but you also have some kind of models, okay, in those built in those models, and you are trying to use all these together, and then you discretize on your computer. There may be discretization error also there, okay, and then you're using different kind of schemes. The schemes may have some dissipation error also. You are reading about listening about the dissipation error now. Okay, so all these things come together. Okay, so it's not like you have the equation and you're getting the exact solution of the equation. Okay, so you may have some error in the dispersion or the dissipation, or your model may not be accurate for the kind of flow that you're simulating, right? We just talked about the continuum and non-continuum things. Right. For example, we also use the ideal gas equation. It may not be the ideal gas which you are trying to model, right? Trying to simulate. So considering all these facts, it's a good idea that we first validate our CFD code with an experimental data, and we see that we are getting a good validation, because that validates many things. Our equations are correct; they are implemented well in your code. Okay, the schemes that you have selected are reasonably good. Okay, and the errors are you're getting are basically within acceptable limit. So all these things are checked, and also you have to check some for some consistency also. For example, let's say if you refine the grid, that means your solution should become better, whether that is happening or not. So all these things you need to take together, and then you see whether your code is doing well. And then after that, you can use the code for other flows also, for which you may not have the experimental data. So you started your code validating with experimental data, but then you will use this code to basically use simulate for the off design conditions also, for which you may not have them not have the experimental data, but still you believe that your code, the solution of your code is good. I mean, it is accurate enough. Right. So these are the things that you need to consider, that uh, the effect of schemes, effect of your model should be basically measured, I guess, in experimental data, good experimental data. I'm not saying that experimental data may not have errors. They also may have errors, right? So that's why you need to basically select the data which are well validated and which are basically known to give good solutions. Okay, so this is regarding CFD and experimental data. Okay, there was one question a couple of days back, and that is like, yeah, that I have already responded. That when you are comparing uh, the conserved quantity with the primitive quantity, right? So we have seen that when you use the conserved form of equation, right? So it actually leads to telescopic log collapse, right? When you use the flux form. Right. If you don't use the form, if you use the primitive form, then what will happen that you don't know whether you should use the backward difference or the forward difference for the multiplying quantities. Right. For example, let's say you are trying to solve del rho u, or let's say do del u v by del x, right? Then it will become u del u v by del x and plus v del u by del x, right? So for del u by del x, you will have may use upwind. For del u by del x, you may use upwind. But what about the multiplying quantity? Right, the u and v, right? Whether you should use the value ui minus 1, ui or ui plus 1. And what about v? Right, so if you do all these things together, first of all, it is not very consistent. Secondly, it will not give the telescopic collapse. That means the flux that you're calculating, the overall flux between boundary to boundary, I mean, all the internal fluxes should go to zero if you do boundary to boundary. Right, the flow is coming in from here and going out from here, right? So in between, whatever thing is happening, that should not be affecting your boundaries, right? But that you will only see when you use the conserved form, not the primitive form. Okay, so these are the questions that I received on the discussion forum, and I thought I'll respond to those. Now let's see. I have some questions on the chat. Okay. Yeah, please suggest a textbook that also deals with coding also, like for different schemes. I can understand all the CFD theory, but I have no exposure to coding. Okay, so that's why, Arpan, I'm taking very small problems. Let's say, I think in the next couple of weeks, you will start doing coding for very simple problems. Okay, so the Navier-Stokes equation is a very complicated equation, as you know. It has got the temporal term, it has got the convective flux term, the viscous term, the pressure gradient term, all those things are there. And then you have a series of equations. You have the continuity equation, momentum conservation, energy conservation. It becomes quite complicated if you are a beginner, right? So why not break this code into very small, break this code into very small things, understand how the code works for those small schemes, those small problems, and then you try the Navier-Stokes. So what you can do, you can take the first of all the convection problem, right? So del u by del t plus cu del u by del x equal to 0. That's your linear convection. You can code it very easily using your favorite software like MATLAB, right? You have the access of MATLAB, I believe. Right, so you just have to use any, let's say, forward differencing scheme for the time. You've discussed that. You can use, let's say, the the backward difference in your space and try solving it for a given initial condition. It can be sine wave or it can be a square wave, whatever thing you take, and you see how it is converting. Right. Similarly, you can increase the complexity, go to the nonlinear problem, nonlinear convection, del u by del t plus u del u by del x equal to 0. Right. That's your second level of complexity. You can go solve the diffusion problem. Right. So let's say del to u by del x square is equal to 0. I mean, you can start with the temperature conduction equation, the heat conduction equation. Right. So once you solve this, then you increase the complexity, go to the nonlinear convection diffusion equation where you have both the convection and the diffusion. And then you go to basically Euler's equation. You don't have any viscous term because viscous terms are complicated. And then ultimately go to the Navier-Stokes. First you try for 1D, then 2D for 3D, and then 3D. So this is the way you should go. Okay. First you should gain confidence that you're able to solve very simple problems on 1D and 2D. And then you can try writing the full code. Okay. So there are many codes available online. Okay. I can't give you one resource, but if you go to GitHub and just ask for a CFD code, you will get plenty of CFD codes. And the best way to learn about CFD is basically start coding. Okay. Write small codes, look at the accuracy. If you have a theoretical solution, compared with the theoretical simulation, and that is how you will learn coding. Okay. And if you learn coding, even you may not plan to write a full-fledged CFD code, it is always useful to understand what is happening in a CFD software. Okay, so that's why I request you to basically start coding different schemes. Okay, there is a question by Yes Gupta. Refining the grid will bring more error terms, increasing the total error. No, it will not. If it is bringing more error, then it's not a consistent scheme. Okay. If you are making the delta x to 0 towards going towards 0 or delta y to going towards 0, it should basically become closer to your theoretical model. Right. It's a basic definition of calculus, right? So your del u by del t is equal to limit delta t tends to 0, delta u by delta t, right? So when delta t goes to 0, right, it should become your the partial derivative, your theoretical right. So if you refine the grid, usually, okay, if your grid is, follows all the rules of making grid, for example, you should have the bondular grid near the wall, and your aspect ratio should be below certain level, the grid quality should be good. So if you follow all these rules, if you are increasing the grid resolution, okay, it should give you the better solution, and if not better, at least the same solution that you got from the course grid. It cannot give you the bad solution. Okay, it can give you bad solution. Let's say now in the first iteration you did the very good modular mesh, and now this time you remove the modular mesh, but increase the mesh size somewhere here, and you are saying that I've refined the grid, right? But you're not following basically what the flow is trying to tell you. The flow is trying to tell you that I have more gradient towards the wall, so I need more grid points near the wall. Right. So if you follow all these rules, then definitely, if you refine the grid, you will go towards better solution. Okay, Deepan is saying that I'm using ANSYS for preparation. That's fine. That's perfectly fine. Okay, ANSYS Fluent is a nice tool. You can use that for your simulations. All I'm trying to tell you through this course is that you should know what boundary conditions you're using, how you should make your grid, what are the schemes you should choose, and how to know whether the solution is good enough for your work, right? So that is what we'll learn from this particular course. Okay, will this lead to generation of more elements? That is increase of, let's say, I think this is the continuation of the earlier question. Will this lead to generation of more elements? That is increase in element size. Okay, when I say grid refinement, I am not, the element size is actually going down. Number of grid points is increasing. Okay, so let's say I have a box of 1 meter cross 1 meter, and I'm using 10 cross 10, right? The grid. So now your each box will be 0.1 cross 0.1 meter, right? Now you let's say that you are going to make it 100 cross 100. So I'm defining the grid. So my number of grid points change from 100 to 10,000, right? Now your grid size is 0.001 multiplied by 0.001 meter, right? So you see the element size has decreased actually, and the grid size has increased. So when I say grid refinement, that your number of grid points is increasing. Okay, that's what I mean by the grid refinement. If your element size is increasing, that is actually grid coarsening. That is not grid refinement. Okay. So Deepak is asking, should I practice more CAD models to practice? Okay, CAD model is for the geometry, right? So let's say you want to solve flow over a turbine blade or flow over an aircraft or let's say flow over a propeller. So then you require precise model that precise geometry, right? So you'll get the geometry from there, but then you have to make an external boundary around that. Okay, and then you have to create a mesh. This is respecting all the rules that I talked about, like the bond layer mesh and how the meshes should jump from the bond layer to the external region, whether you're taking care of the bond weaknesses or not. Okay, the mesh should not be overlapping on one another. So that then you create a mesh, and when you create a good mesh, then you have to worry about the bonding conditions. You have to select a system of equations that you're going to solve, whether you're going for the incompressible or compressible. Okay, if it is compressible, whether you're going for ideal gas, how the viscosity is changing, how the thermal conductivity is changing. If it is flow is turbulent, what kind of turbulence model you should use. So I'll talk about the turbulence model also in this course. Okay, so the CAD model is just a starting point for a CFD engineer. Okay, that can be provided also by your, let's say if you are working in a company, your, the customer you are working for, they will provide you the CAD model and ask you to do the CFD simulation. So after you get the CAD model, you have to figure out how to create a mesh. Okay, first you have to make it watertight also. Basically, it should not be leaking from anywhere. Okay, the model. And then create the mesh and all the steps that I told you. Right, and then you ultimately do the simulation and finally you do the post processing. Okay, so I would rather suggest that you can, for this course, you can take very simple models, simple problems like I've been talking about the lift driven cavity problem. You can do flow in a channel, okay, and many different problems like short soft tube will be talking. Okay, and we'll take many simple problems. If you have understanding of CFD through the CFD problems, I'm sure you can extend your ideas for more complex problems. These ideas that you will be learning. Okay. Next question is from Ashwin Manoj. How to validate simulation models with hand calculation? Are we simulating to reduce time, right? I mean, there are two reasons. I have given like a couple of lectures about why CFD is important. Of course, it reduces time. So take a very simple problem. Let's say you are solving a system of equations. If 2 equation 2 variable, you solve very easily. If 3 equation 3 variable, it will take some time. If I give you 4 equation 4 variable, 5 equation 5 variable, then you would say rather I will go and look at in the code, right? Look at in the MATLAB. You will give uh, uh, the equations there and get the solution from there. Similarly, you can think of CFD. Okay, so if you have a very simple problem, you can probably do the hand calculation and get some estimate. But when the problem becomes complex, okay, you want the computer to solve those problems for you. Okay, once you have related for a simple problem or a simple small geometry. Okay, so that is where the CFD becomes very useful. Uh, so regarding the hand calculation, so I will show you like for some of the small problems, you have the theoretical results available and you can directly compare against them. Okay, but when the problem becomes complex, you don't have any hand calculated results. You have to either rely on the experimental data or you have to look at some kind of consistency within your simulation. Like as I told that you do the grid refinement, whether the solution is staying the same or it is changing, all those kind of things you can do. So how to determine where in the domain the mesh should be made fine or coarse? Right. So I have actually, I just told that you have to understand the flow. If you understand the flow, then you can easily answer these questions. Right. For example, let's say you are solving flow in a channel or flow in a pipe. Right. What will happen near the pipe? Near the pipe, your velocity is on the pipe, the velocity is going to be zero. Right. Within the pipe, it is flowing with some velocity. Now the velocity will change from whatever central line velocity you have to the wall, the pipe wall, right? And near the pipe wall, you are going to have very high shear. That means the velocity is changing very rapidly. Your on the wall, on the pipe, the value is zero, but on the next point, the value is not zero, right? So you have to have a very fine layer very close to the wall. So that is the first approximation. That is something you should know, that this is the region of high shear. Most of the activities are happening here. Okay, most of the your genetic vortices and so many other things there. So you have to refine those regions. So if you know the problem, know the flow, how it is happening, you can do those kind of things. Similarly, let's say you are doing a jet flow. Okay, the flow is coming out of a jet. Right. So where the flow is coming out, you are going to have more activities there, right? The far field, you may not have much activity. So you have to make more refined grid here. Right. So these are the concepts you have to use when you are trying to solve a problem, because it gives you an idea that these are the regions where the flow, more activities are happening in the flow. And if you have taken any fluid dynamics course, and I am sure that you must have taken, if you have not taken, I would strongly suggest that take some fluid dynamics course, especially one in the basic fluid dynamics and then one in turbulent flow. Okay. So how the turbulent flow changes, how the bond layer in the turbulent flow and how it is different from the bond in the laminar flow. Right. So if you know the behavior, if you look at the turbulent flow, you might be knowing about the law of the wall. Right. So if the y plus is less than 5, then u plus is equal to y plus. Then beyond that, there is certain region where your it goes as a logarithm of y plus. U plus goes as logarithm of y plus. Yeah, that's called a log law. Okay. And then you have basically the outer layer. So let's say if you are resolving u plus equal to y plus, that is the very close region to the wall, then you must have at least 5 grid points to resolve that, right? You are going from 1 to 5, y plus equal to 1 to 5. At least you will have 5 points that will give you a line u plus equal to y plus. Similarly, if you are resolving log layer, you have to have some n number of points to basically resolve the log layer also. There are some models that you may think of. If there's a wall function, then the refinement may not be that necessary near the wall. I mean, refinement will be necessary, but the first grid point may not be that small if you are compared to if you are going to solve to the wall, right? Where you are resolving all the viscous sublayer and then log layer and all those regions. Okay. Okay. So then I don't see any question here now. Okay. If you have more questions, please ask, because otherwise I believe I have answered all the questions. Anyone else? So we'll keep doing these kind of sessions, let's say once in a month or once in a couple of months. So if you have doubts, please feel free to ask. Okay, there is a question by Shreyas Kundu. In CFD, how do we decide which turbulence model to choose? Okay, so I'll come to that. Okay, so please wait. I will have at least 1 week of full lectures on turbulence models. Okay, so I will discuss about different turbulence models, which turbulence models are good for what kind of flows, and which are if the flow is transitional, if the flow has got separation, or it has got shocks, then what kind of turbulence model we should use. So we'll be discussing those. Sir, will you cover coding for shock waves? Yeah, so it's a compulsory flow course. In fact, my first example would be a short shock tube. Okay, so the shocks will form, expansion waves will form. Okay, so we'll definitely have the cases with shock waves. Anyone else? Okay. So the question is, sir, the adaptive mesh refinement shall make the code more complex. You have to keep track of the interface. So it will be more of a Lagrangian approach. No, no, no. So adaptive mesh refinement, Lagrangian approach is particle tracking. Okay. So you are basically tracking each particle. Okay. Adaptive mesh refinement, I'm not sure if others are familiar with this term, is that basically it's also called AMR in short form. Okay, so let's say that at some place. So initially you don't know where let's take the example of a sock, right? You don't know where the sock is forming, right? Now the sock is formed, right? So you want to see a better behavior of the sock there. So you go and refine the mesh more near the sock, right? So what we are doing is gradually refining the mesh depending on where more activities are happening. Okay, so if it is wherever more activity, you are basically defining the mesh there locally. So that is your adaptive mesh refinement. So it is nothing, it has got nothing to do with the Lagrangian approach. It's just that you are looking at activity and based on that you are refining the mesh. Okay. Anyone else? You can unmute and ask question. Okay, you don't have to put on chat box only. You can unmute and ask questions. Okay, there was one in the feedback form also. Let me just see that question. Yeah. So good evening, sir. I have to see your, I like to see your classes and teaching method. I have one question: how can we connect the concept of theoretical approaches of CFD and simulation approach of CFD? What was the core behind the concept? Okay. So that is the purpose of this course, that I want to give you the theoretical background behind CFD. Okay, there are many courses, many codes available through on the internet which can tell you this is the equation, this is how I coded in finite difference. But not many will tell you, let's say if you use this scheme or that scheme, what is the difference that is going to get? Okay, or why this scheme is more stable, why this scheme is less stable. Or let's say if you're using convection equation and if you use a central differential scheme, what will happen? Right? If you are adding diffusion, how much diffusion you should add so that you are not losing the accuracy too much and still able to still you are able to simulate the flow. Right. So all these things require some of the theoretical consideration. There is a good, well-built theory behind whatever scheme that you're using. Okay. So my approach in this course is to basically give the background or give the exposure of those theoretical approaches to you, so that you have a good understanding of CFD. And of course, as somebody was asking that you learn better by coding, okay, by experiencing it yourself. I will give you some examples. I'll show you the plots on my PPT, or maybe I'll walk you through the code also. But that will be like only a few times. If you want to really understand how things are changing, how the different schemes behave, what is the effect of changing the grid size, changing the time step size, changing the scheme altogether, adding the diffusion, adding the dispersion term. I suggest that you follow my lectures and also code at your own time, okay, in your home. Okay. There is another. So that I will make the code. Okay, this. So our grid will have to keep a track of the stock, as you said, sir. No, I'm not going to talk about adapting mesh refinement in this particular course. Okay. So you in my course, it will be simple. You can do the simulation with the course grid, then you refine the grid, okay, and do the simulation, then you define the grid and do the simulation. Basically, once you refine the grid, you do the simulation on that. You are not changing the mesh while doing the simulation. Okay, so that is not necessary, right? You can do that. The adaptive mesh refinement, okay, to basically resolve certain flow features. But if you can make your mesh fine enough that you are anyway resolving those flow features, then AMR is not necessary. Okay, it's a good approach, but we will not be covering that in our course. Okay. So will we study about transionic flow simulation CFD? Yeah, it's a compressible flow case, right? So it covers the entire regime from the subsonic to transonic to supersonic to hypersonic. So, if you want to know how the transionic flow works, then you have to take a different course in the transionic flow itself. Okay, but mm, otherwise, the equation, the governing equations remain the same. Okay, so the transionic flow may result or may not result in shocks, right? So that you will get from by solving the problem using the CFD code. Okay? So the theory of the CFD remains the same, but for the theory of how the shock waves are formed, how they travel, okay, what is the difference in transonic condition, subsonic and supersonic conditions. For that, you need to refer to a different course or a textbook. Okay. Anyone else? Okay, so if there are no further questions, Let me just see if I have some more questions on the discussion forum or the form. Okay, so looks like uh, no more questions. Okay, so okay, there is one on. Okay, YouTube. There are some participants watching. So if you are there, if you have any question, please put in the chat box. I can see it there and I can respond there. Okay. So if there are no questions, then I would sincerely request you for your feedback because I'm teaching this course for the first time. I've actually taught this course already in my institute, but for NPTEL, because you have a large audience and you may have different requirements, and I would basically try to satisfy or try to basically meet your requirements as much as possible within the time constraint. Okay, so please give your feedback, whatever questions you have. You can ask from the forum, you can ask during the live sessions. So next time probably I'll keep the live session on a weekend, maybe Saturday, if that is more suitable for you guys. Okay, so please feel free to provide a feedback how to improve the course. If there is certain thing that you want to ask, okay, you want me to add, okay, I'll be definitely willing to consider those things. Okay. Yeah. So Murli is asking me to wait for a few minutes. I'll wait for a few minutes. If there are a few questions, I will definitely, I'll be happy to answer. So one more thing I would sincerely request you, those who are watching or those who will be watching it later, is that make your foundations of fluid dynamics strong. That is very, very important. Okay, if your foundations in fluid dynamics is not strong, you will be struggling in CFD. You might be able to solve some problem, but you will be struggling with some other problem and you will not be knowing why it is not working. So CFD is basically computational fluid dynamics. So you can compute a flow only if you understand what is going to happen in the flow. Right. So you should have the broad feeling before even if you start CFD, you should have a broad feeling of how the flow is going to evolve. Okay. For example, if I can, if you have read fluid dynamics, you will know that you cannot have a shock at when the Mach number is let's say below 0.8 or below 0.7. Right. So subsonic flow cannot result in formation of a shock. Right. But if it is in transonic condition or in supersonic, you are expecting shocks. So you're already expecting the behavior. Right. So accordingly, you can use your scheme. Some schemes are not made to capture shocks. Some schemes are made to capture shocks. Right. So if you understand your fluid dynamics, then it will be easy to use CFD for the simulations. Okay. Not only that, even the boundary conditions. Okay. The boundary condition is a very, very critical thing in CFD. Okay. I'll touch upon that also. So if there are many boundary conditions. So what do you mean the pressure inlet, the velocity inlet, and then you will have characteristic boundary conditions, ball boundary conditions, where to apply what kind of boundary conditions. So all this comes from your understanding of your theoretical fluid dynamics. Okay. And as I've been telling you since the beginning, is that think of CFD as a numerical wind tunnel. Okay. So for example, I'm sitting here, there is a flow happening, there is a fan running and there is a flow happening. Right. So if I want to model this, then I have to basically find out the speed of the fan, the distance from me to the wall, the temperature, which is what is there in the room, what kind of modes of transfer, heat transfer that may happen. All these things, if you combine together, you'll be able to solve the problem that how the temperature is, let's say, varying within the room. Right. So all these things require you to think that uh, how it would happen if you were doing an experiment, right? And from that you infer that okay, this is the one you can say that I should be using for the CFD. Okay. Yeah, so there are no questions on YouTube. If the Zoom participants have any questions, please ask the question. Okay. If not, then we can probably close it. Okay. So we have two TAs for this course. One of the TAs has joined this meeting today. So we have Mr. Vishal Sethi, okay, who is the primary TA for this course, and he is also responding to many of your questions, queries on the discussion forum. Okay, we have another TA, which is Miss Gemini Chauhan. She has not joined, she might have some class or something. Okay, so they are basically taking care of course, I mean running the course. So if you have any question, any doubts, or let's say you are not able to see some material or some YouTube video, or you like to have some additional references, or whatever questions you have, maybe related to the quality of the video or quality of the notes that you're providing, please feel free to contact them. They'll be happy to help you. Okay, so yeah, once again, thank you very much. Who could join today, and I hope that we'll have more participants in the next session. And if you have any question, please feel free to ask. Okay, send it to the discussion forum. And if you want to basically ask it personally during the live session, we'll be meeting at least once in a couple of months. So we'll be meeting at least 2 to 3 times in this course. Okay, so you can hold on those questions and we can try to answer you. But if there is something urgent and then that you are not able to follow certain lectures, okay, definitely you are welcome to ask the questions in the forum and we'll be happy to respond you in a time. Okay. So thank you very much. And thank you, Murliji, Tarunji, Vishal, and all the participants. I can see Gayatri, Arpan, and Twaha. Okay, so thank you very much for joining.